Earbuds. Let's get them earbuds out. Buds. I don't like calling you bud. I'm not going to do that again. All right. So here we are. We saw that Newton had this thought that, man, if I throw something hard enough, it's going to bonk me in the back of the head. And it's reasonable to think this. Now, going through the immediate follow-up on this idea, and we're still in 7.2. We're going to be for several days, just so you're aware. I'm going to check the color. We had orbit thought experiment, and that's Newton's big idea. And we're going to expand on that. So velocity feels kind of red to me, so let's use that. We are going to go into discussing a satellite's speed. Now, I'm going to call it velocity because it bugs me when we call it speed. What's the difference between speed and velocity? Mickey, I haven't called on you today, and we made eye contact there for a moment. What's the difference between speed and velocity? Okay? While Mickey's thinking, if you don't know the answer, I want you thinking or chatting with your neighbors as well. There is a difference. Speed and velocity. All right, so Mickey's digging through. Not a lot of other people are, which makes me think you automatically know it. Somebody give it, hook it up. What's the difference? Abigail, I haven't called on you yet. Do you know? There's no direction with speed. So with velocity, I am going to use direction. But let's find it. Now, we might really be talking about speed because in orbital motion, direction's a weird idea. You know which way it's accelerating, right? I think, but we'll check. So let's just start right there. If we have a satellite, and whether it's this ball that Newton threw or whatever the case is, it's being accelerated if it's orbiting. Okay, now it could be moving at a constant speed, but I'd say it's not a constant velocity because the direction is always changing. What's causing it to orbit? Too many people at once. Fern's got it. Cool. What makes a satellite orbit our Earth? Gravity. Okay. So gravity is the agent that causes what sort of force that pulls toward the center of our planet? Centripetal. So right off the bat, I know that if something's accelerating, it has orbiting, it has centripetal acceleration. It has to. So let's do a couple things, and I'm going to try to be specific with colors here. Centripetal acceleration. How on earth do we find centripetal acceleration? You take the velocity, you square it, and then you divide it by r. Cool. I'm good with that. And then let's go one step further. I'm just going to use a semicolon to separate them. There's a centripetal force that's acting on this. I'm going to call it net force. But how do you find the force acting on some object? So Nick, I'll teach you how to do it here in a minute, but I want you to make sure you're here too. Be present. Cool. A little hippie language. How do you find net force? Good. Now in this case, it's centripetal acceleration, so I'm just going to say it's mass times centripetal acceleration. Everybody's still on the same page. Now, is there any way that we could substitute some stuff in here? Like, if I wanted to, I think that I can reasonably say that, all right, my net force is exactly equal to mass, and I already know it's centripetal acceleration, but how did we find centripetal acceleration? So check it out. A little bit of substitution. Here we are. I have mass times v squared over r, and I'll rearrange it here in a second. But I haven't done anything too crazy. We're just saying, hey, look, these are different ways to calculate it. Let's substitute in. Now, we are going to hook Newton up to this problem. And I'm just going to say, between these lines, let's use, and I have a new abbreviation. What's n log? We called it nug the other day, but this is better. So check your notes. I guarantee we'll find it. Whoa, you got it. Newton's law of universal gravitation. Now, it's gravity that causes that centripetal force, right? And assuming that that's the only thing acting on this, Newton's law of universal gravitation is the cause of that net force acting. So, let's go one step further. We know that the net force acting on this object on Earth, orbiting around Earth for this example, we can use Newton's law of universal gravitation. So here we go. I know that Newton's law of gravitation reads that the gravitational constant, m, or g, weird. And then we have an object orbiting Earth. So I'm going to say one of those objects is Earth, me. And let's just say that the other object, the satellite, has a mass m. We don't know the number yet. So here's g m1, m2 with mass of the Earth and the mass of the satellite over, what do we divide by for Newton? It's the inverse square law. The inverse square of what? Radius. So because the only net force acting on my satellite just happens to be, you know, this fancy gravity, we get this expression. And I'm going to start struggling with my colors here pretty quick. M, and I'm going to write this as a single fraction, v squared over r. Have I lost anybody in this process? Just to be super duper clear, why am I allowed to take this and replace it with this? Talk it out with your neighbors quietly for a second. So, oh, Tolly's got it. Can you try this one first? Or ask out loud. I'm good with it. 100%. The only thing causing the satellite to orbit is just gravity. And here's how we calculate out the force of gravity. Cool. Was that your question, or were you just answering that? Did you have a different question? Oh, that's also fine. Okay, so here's what I want you guys to do. We're going to play the algebra game. Flex those muscles just a skosh. What are we trying to find? Like this whole section, what's like the whole point of this? We're trying to find how a satellite does what? Or what about a satellite? It's velocity. So here we go. Little algebra. Solve for v. And we're going to pause this. I'm going to give you guys a head start. Practice the algebra. Cool. We'll meet up in like a minute. I think this is it. Can somebody confirm that? Baller. So, this is obnoxious, but it's important. So I'm going to do this. This is, whoop, too much. This is an important idea. Bunch of stars. That's how important it is. Okay, we now have this expression right here. V equals the square root of the gravitational constant times the mass of the Earth divided by the radius. What is this telling us? Like if I use this to calculate v, I'm finding the velocity of what? A satellite. Now, just thinking this out, if we look at this, we could play the unit game. Do you have any anticipation for what this unit will be? How do you measure velocity with SI units? This is meters. So per second squared is acceleration, but I think that you caught that as soon as I started talking. This is in meters per second. Now, as we go through here, I don't think I'm going to write it down. G is what? Not a number, but what is it conceptually? The gravitational constant. Me is what? Other than baller. The mass of the Earth, and what's this? What radius? So not quite. Kind of. And we'll talk about this. And we'll make sense of this here in just a moment. Actually, we'll just do it right now. If we have Earth, and there's a satellite out here orbiting, we said that this is the height or the altitude that it orbits at, right? But where do we see gravitational attraction between what part of Earth and whatever it's attracting to? So that radius is from the center of our planet, or whatever planet, in this case it's Earth, all the way out to that satellite, which means we're going to have to use this radius of Earth pretty regularly. Cool. Now, in reality, do you think that this is really true, that it's exactly from the center? Or does it continuously create gravity at different strengths as you move away? The second one, but it requires a lot of fancy calculus to be able to actually do those calculations. Cool. We have it. Now, is this important? For sure, hence all the wonderful stars. Now, one more little follow-up on this, and this isn't a big extension because we've already seen this. If we talk about the speed or the velocity, that's certainly one thing that we've seen before. We wonder how fast is this going. But if I have a satellite that's orbiting the Earth, other than how fast is it going, another natural question is how long does it take? So we need an orbital period as well. Now, this one, we're going to say orbital period of a satellite. Orbital period of satellite. Okay. Do we have a formula for orbital period of something orbiting like the sun already? Have we ever done t equals some big expression? Now, you may not remember it off the top of your head because I struggle to as well. But if you check from the work that we did earlier, the homework you handed in, the notes from any day before today, I think it starts with 2 pi times something. The square root of r cubed over g and me, right? Morning. Your hair looks super cool today. Now, as we're looking at this, a couple things that I want to highlight here that it's entirely up to you. There's something that kind of annoys me about that. Is there anything that kind of annoys you about that? Any part of it algebraically, pure mathematically, that's annoying about that final expression we just wrote? Okay, we're going to put on our math hats for just a second. Anything annoy you about this? Root 18. I can hear the gears turning. What's 18 made of? What are its factors? 6 and 3 is an okay choice. There's a better one. Why is that better, Riley? This is the real answer. What's annoying about this? What's the square root of r cubed? And that's a weird question. If you wanted to, and it's entirely up to you, but I just want to in red, so it's up to you if you want to. Could we call this 2 pi r times the square root of what stays inside? Not if we took an r squared out of r cubed. It'd just be r, wouldn't it? If you would rather plug this in, you're welcome to. On a calculator, I don't think it really matters. If you're going to cube it here or take it out, doesn't matter to me. Be okay with either. I think I'll probably just use this one. Cool. All right, so we get to do a problem. Now, if we want to use these formulas, either the velocity, and hold on, grass is a fundamental part of life on our planet, right? Like, we need grass, so that's also an important idea. This one's also important. Cool. These two formulas, if you were going to add anything to your cheat sheet, it would probably be these. All right. The eagle has landed, just for the record, in our spy talk. Cool. Let's do a problem. So, I don't want to write the problem. When we have a bunch of them, I'll continue making worksheets, but not everybody likes worksheets, and I totally get it. I want you guys to open up your book to page 188, and then with a piece of paper, and this is a challenge. I didn't want to just do a completely different problem, but I didn't want to have to print out a thing for just one thing either. So check it out. We are going to work the problem on page 188. It's called example problem 2, but I want everybody to do me a favor. The favor that I would like you to do is on this page, here's this problem. I want you to take your notebook as we're working this problem, go ahead and just put it right there so that all you see is the question itself. Don't give yourself the answers, like, let's see if we can't think through this. So here we go. We have a satellite orbiting Earth 225 kilometers above Earth. So it's pretty high up in the sky there, and I'm just going to copy this down. You guys do not have to. The way that I have this in my notes, you'll see it, example problem 2 on page 188 is just how I named it. So here we go. We have an orbital speed of a satellite. And I'm just going to copy and paste that eventually. I wish I'd shown you guys that before I got rid of it, because Keisha drew a really wonderful moon. But it's gone forever now, so cool. Alright, get out of here, folks. And camera is actually what I meant. Sweet. So, couple things that we need, and I think they hook it up with, they tell us the gravity and or the radius and mass and all that stuff. But let's check. So we'll put it right there. Alright, so here's our example. We are asked to find the orbital speed and the period of some satellite that's orbiting Earth there. Now, as we look at it, if you want a picture, you can draw it, but I don't know that it's a huge issue. I'm going to leave space and we'll draw it if we need to, but let's go ahead and just write out what we know and make sure we can label them correctly. I know the height of my satellite, right? Now, has the word height or altitude or anything like that shown up in any of the formulas that we've seen? No. So we're going to have to build up to that, and I think we can reason it out. And if we need a picture to get that, we will. But let's look. Do we know the radius of Earth? Okay, it's huge, right? 6.38 times 10 to the 6th meters. Okay, big old planet. What else do we know? So I know its orbit, kind of, right? I know its height. So I hate this, but I'm going to go ahead and say height equals, would you write 225 kilometers? And why am I apprehensive about writing 225 kilometers? Because there's meters up there. How do we change that to kilometers? Or sorry, to meters. If we divide by what? So if I say that 225 kilometers is 0.225 meters, do you agree with that? Like that's that's backward, right? That's times. So a couple ways we can do this. You can write out 225,000, or I can just do 2.25 times 10 to the 5th. That assures me I get 225, and then 3 more gets me to the 1,000. So we have that value given. Anything else? What are we orbiting? We're orbiting the Earth, right? And gravity is directly related to the mass of an object, so we should probably record the mass of the Earth. A bit smaller than the Sun. 5.97 times 10 to the 24. Okay, now the picture, whether you draw it or not, and we just discussed it, but I want to make sure it's super duper clear. Here's Earth, he's pretty cool. Here's our satellite, also pretty cool. This distance that we just found is my 2.25 times 10 to the 5th. Is that the radius r that we need? Because I'm missing that whole distance, right? And what's that dashed distance that I just indicated? It's the radius of what? The Earth. So when I look at this, it's not truly a known, but we have all the information to find it already, so I'm going to count it as a known. If I want the entire distance r, this guy, what do I need to add together? I need the radius of Earth plus the height. Now, don't just add them together. It's really easy to want to do that, but the powers are different. I have no issue if you convert it, like move all the decimals and then do it, or you just ask your calculator, but it is not just going to be your 8.63 times 10 to the, like we wouldn't have the power. I want you to verify, but I think that we wind up with 6.6 times 10 to the 5th. Once you guys seemingly are trusting me, Fern will verify whether that's true or not. Cool. All right. Your assignment tonight is a little bit of practice. You need to find from this information, I want you to find me the orbital period t and the orbital velocity v. Or we can call it speed, but I'm going to call it v. Cool. That's your assignment. Peace out.